Yeah, also very warm welcome from my side, and exciting to be here on PyCon. Exciting to be here on stage, and I'm very happy to talk about open table formats today because I think they represent a technology that has changed the data engineering landscape in recent years to the better. But before we get into the very detail, let me quickly outline the agenda of the talk. First of all, I want to start with a brief moment of thinking about why data is important at all. Why are we here? Why care about storing data? Isn't that a boring topic? Turns out it's actually not. And then I would like to invite you to two histories. One history lasting 100 years, a century of development of printing machines, and a related history lasting only 10 years, which describes the very first big data platform that we used in my company. And this already introduces us to Apache Parquet. We will then deep dive on Apache Parquet and see and understand how Apache Parquet works. But we will also showcase the issues that Apache Parquet didn't solve, which essentially gave birth to the existence of open table formats such as Delta Lake, Iceberg, Hudi, or also Apache Payman. And then, understanding all the promises that open table formats have made, we want to put a specific open table format, Delta Lake in this case, at a test. Because we thought, well, why not replace our formerly Parquet-based Bronx data layer with an open table format to improve performance, to reduce maintenance, and to gain more flexibility. And it turns out this isn't as easy as we thought it would be, and there's a twist. And it will be very interesting. And in the end, I would like to take a very short moment to talk about the current state of table formats. As I mentioned earlier, there's Delta Lake, there's Hudi, there's Iceberg, there are also other formats such as Apache Payman from the Flink community. And I want to give you my personal opinion on it, since it's currently a very hot topic. So let's kick it off. A 10,000-foot view. It all begins with data. But why? Why are we here? Why is PyData so popular at the moment? Has been popular also in recent years, but just this morning we heard more than 2,000 participants. Well, typically before I start to prepare a talk or a presentation, I ask myself, why is this relevant to me or to you as the audience? Why is it relevant in general? And it kind of struck me after a while that data is at the very core, at the very heart of scientific progress and human advancements. While this may sound or seem obvious once you see it, it is not obvious right from the beginning. When you think about your personal life, when you think about your university studies, you come up with some ideas, you come up with some theories. We as humans, we want to understand our environment, we want to improve our quality of life. And how do we do this? We do this by understanding relationships in the outside and internal world. And coming up with ideas and theories, we somehow have to falsify or validate them. So we need to collect some sort of external criteria that proves our hypothesis to be right or wrong. And this is done by data. We observe and we collect data. And sometimes we have an object of research which is fairly simple. For example, imagine measuring the weight of a stone. Fairly easy. One data point that I can memorize in memory. Or the size of a person, also fairly easy. But there are other examples which are more sophisticated, which are more complex. For example, I have a background in psychology, and in psychology we study human behavior and cognition. And we all know that we are humans, we are so vastly different, there's so much variance, there's so much random error involved, and you need very dedicated questionnaires, dedicated measurement devices, and dedicated statistical methods to reveal a pattern, to gain an insight. And it's all about having data and being data-driven to gain insight, to progress with the scientific research. While this is rather abstract for now, let's take a look at a very clear example, our first 100 years journey. And this is about printing machines. And this is not by accident, it's because I'm working for a company, Heidelberger Druckmaschinen. Heidelberg is the name of a town which is roughly 60 kilometers south of Darmstadt. And Druckmaschinen is the German word for printing machines. And this year we are celebrating our 175th birthday. And I also learned something new during this anniversary, that we didn't start off with producing printing machines, but rather we started off producing belts. For example, one of the original belts in the Cologne Dome was from Heidelberger Druckmaschinen back in the day. But it's not about the history of Heidelberg, it's about the history of those printing machines and how data has affected those machines and their efficiency. On the left side, you can see an original Heidelberger Tiegel, which was developed roughly 100 years ago. And on the right side, you can see the most recent machine. It's called a Speedmaster. And let's compare these two machines on 3 high-level KPIs. The first high-level KPI is the number of sheets printed per hour. The Tiegel on the left could already print 3,000 sheets an hour, which I think is impressive for a machine being 100 years old. The Speedmaster, masters the speed, as the name suggests, prints 21,000 sheets an hour. So this is like a 7 times difference. Now let's take a look at the second high-level KPI, the number of colors applied. The Tiegel on the left side could apply 1 color at a time, whereas the Speedmaster on the right side, you can see those units, and there are 8 of them. There are 4 units, 4 colors applied on one side of the sheet, then the sheet gets turned around, and then another 4 colors applied on the other side of the sheet. And this is a very standard configuration. And you require 4 colors in order to cover the entire color spectrum. So this is an 8 times difference. And now the last high-level KPI is about the sheet size. With the Tiegel, you could roughly print an A3, like this size. With the Speedmaster, you can print A0, like 4 times the size of the Tiegel. And if you multiply all this together, you end up with a 244 times increase in efficiency between those two machines during a period of 100 years. You could also put it differently and say every 10 to 15 years, we double the efficiency. And this did not happen by accident, but it happened because we used data, we used theories. And these machines, you can guess on the left side, the data ingestion or the data tracking was a rather manual process, whereas on the right side, there's lots of sensors inbuilt to automatically collect data and store data. You can think of low-level IoT sensors such as temperatures, currents, speeds, error failure messages, consumption messages, but also high-level KPIs such as in OEE, or the number of good sheets or wasted sheets, make-ready time is everything you can think of. And with the ever-increasing amount of data and the number of increasing machines connected, we are facing an issue on how to store and process all of this data. And this brings us to our next history that we are going to cover, the 10 years journey of the very first big data platform that we used at Heidelberger Druckmaschinen. And back in the day, 2015, 10 years ago, Apache Hadoop was kind of state-of-the-art. So Hadoop, we used an HDFS, distributed file system, to store all the data, and the data was already stored in Parquet format. There was a very wise man who decided to use Parquet because this is something we still use up until today. We then also added Hive to the mix and improved on having a logical table instead of a file-based access. We also used Cassandra and Kudu, but it's not so important. We used Spark as a batch processing engine, and we also used Presto for interactive queries. And fun side fact, with Spark, we still have Spark jobs in production that run in Spark version 1.5. They've been written with Java-based API using the RDDs instead of declarative data frame APIs. And they even included a custom domain-specific language from our external partner. And Toby, one of the guys who wrote these jobs, is also here today, unfortunately not with Heidelberg anymore. But it has been a torture for him and it has been a torture for me to maintain these ones. And I'm very happy if we can shut down this platform by June this year. Why do we shut it down? Well, first of all, with Hadoop, you have a coupled storage and compute. You can't scale your storage independently of compute, which resulted in a scenario where we always moved the data that is older than 2 years to an S3 bucket, to an external bucket that was not stored on the HDFS, because we couldn't scale it independently. You can't just increase compute and storage just like this, as you can do on AWS, for example, or on Google Cloud or on Azure. In our case, this means on Mondays, when most of our customers start their shifts, we get lots of incoming data. Then there's a high peak of processing, and there's a huge backlog that builds up. In contrast, during the weekends, there's no incoming data. The entire platform just idles and wastes money. And there's also another reason why this failed. We as a team, our internal team, also failed to maintain up to the standard and up-to-date frameworks, such as we didn't have a proper, we still don't, up until today, we don't have a proper orchestration framework, such as Airflow or Dexter or Prefect, to model interdependencies between Spark jobs. We don't have infrastructure as code framework to reproducible provision our Spark jobs. This is rather a manual process. And there are many other things that didn't go that well. And well, what we did is probably what most did. We went to the cloud. So we went with AWS in our case. And the cloud world is so full of promises too. For example, it's so easy just to open up an AWS account, create an S3 bucket, and just store tons of data there. And it's cheap. You can even decide, well, I'm not accessing the data that frequent, so I just choose a different storage tier. And then I can spin up whatever compute I like. I can, if I have a very compute-intense job, then I use compute-optimized EC2 instances. If I have a rather memory-intense job, then I just choose some memory-optimized instances, or I can use some GPU instances. Not possible with the traditional Hadoop platform, no way. But, and there's a big but to it, it's not that easy to just move from Hadoop to the cloud, because if you want to orchestrate all those different services that you require for an enterprise platform, this can't be done by a data engineer. It can't be done with a single team. You have to integrate storage, compute, orchestration, monitoring, alerting. Everything has to be testable, reproducible. You need something like authentication, authorization, user provisioning. This is like a whole enterprise project that cannot be done by an average-sized company like Heidelberger Druckmaschinen. And that's why, you know them, other companies have done such things. They have built these integrated data platforms, such as Snowflake and Databricks. And at Heidelberger Druckmaschinen, we actually use both. We use Snowflake and Databricks, and this decision has been made 2 years ago. And why is that the case? Why not just use one of them? Well, back in the day, 2 years ago, Snowflake had a clear edge in regard to warehousing and BI, whereas Databricks had a clear edge when it came to more complex data pipelines with a native Python interface, which require proper testing, introspection, and also the machine learning frameworks integrated in the Databricks platform were way better than Snowflake ones. Nowadays, they consolidate more and more. They get more and more closer regarding their functionality. Snowflake now offers native Python notebooks. Snowflake now even offers a managed Docker runtime. How crazy is this? Whereas Databricks, yeah, they started with Databricks SQL, but they are now also competing in the warehouse space. And Databricks also now offers like a complete serverless setup. You don't even have to touch any AWS resources anymore if you want to run Databricks. So they're getting closer and closer together. But besides Databricks and Snowflake, well, if you're interested, come to our booth. We love to talk about this. But besides these two, Parquet persisted. We still use Parquet today. So let's say, hey, say hello to Parquet again, and understand why Parquet is superior to CSV or JSON for analytical workloads. Why is that the case? Why is JSON and CSV guys looking jealously at the Parquet hugging the data here? Well, for one, Parquet supports strict types. This is not the case with CSV. It can be the case with JSON if you use JSON schema, for example. But strict types, they offer a huge benefit. First of all, they convey meaning. And secondly, they remove any serialization and deserialization issues. When I started with Heidelberger Druckmaschinen as a data scientist 8 years ago, I needed to write tests for my Spark data pipelines. And I needed a format that can also communicate with non-technical users. So I couldn't say use Parquet, for example, back in the day, but rather, okay, here's Excel. Everyone can use Excel. Please provide your test data in Excel. But then I had to get this Excel data into Spark. And this was a hell. It was even before Pandas 1.0. So this meant using Pandas to load Excel. You get a hell of type conversions with timestamps, for example, or even strings. And then I had to convert Pandas data types into Spark data types. This was also a hell. And then to do the testing, Spark back in the day did not offer a native way to compare data frame equality, which is kind of surprising. Pandas did have a possibility for this, but Spark not. So I had to convert it from a Spark data frame back to Pandas to finally test data frame equality. And there was so much boilerplate code just involved to test. Anyways, the next benefit, efficient encodings. Parquet offers a whole lot of built-in encodings, such as dictionary encodings, bitcasting, bit packing, sorry, not bitcasting, bit packing, run length encoding, and you can even chain them together. For example, if you have a string column, why store these expensive UTF-8 strings or characters? Rather just map them to numbers, use a dictionary encoding, and let the CPU crunch with numbers for your group by aggregate query. And then, for example, if you have a string that has lots of consecutive repetitions, And then you can add a run length encoding on top of the dictionary encoding, saving more space and making your CPUs run faster, typically. And the last one, Parquet files are splittable, which we will also see shortly. That means if you have a multi-core setup, you can process a Parquet file in parallel instead of, for example, having a JSON, try to split a JSON in part. Or if you have a gzip CSV, try to do this. It doesn't work. But I think the most striking feature that Parquet added here was the possibility to skip irrelevant data. And now I want you and me to assume a role of a Parquet writer application. On the left side, we have an in-memory data frame, 3 columns and 6 rows. And we will now follow the Parquet writer specification, or the Parquet memory layout. So the first thing we do is that we partition our data horizontally. We create row groups, groups of rows. Next, we partition vertically. That means we take column chunks out of these row groups and we store them sequentially on disk. And this is important. Typically, we say Parquet is a columnar-oriented file format. And yes, it's columnar-oriented, but also we split horizontally here. We have row groups and we have those column chunks. And why is that the case? We are talking about analytical workloads. We're interested not just in a single row, but rather we're interested in entire columns spanning a long history. There are no CRUD operations involved in our analytical workloads. But rather, you have a filter condition on one column and an aggregate clause on the other column. And hence, you want to access entire columns. But also, you want to have these columns to be co-located. If columns are stored somewhere else, then still you have to read large chunks of your data. But in this case, we have kind of a sweet spot. We say we have columnar layout, but also row groups splitted horizontally. So we chunk these columns, A, B, and C, and while writing out the data, we collect statistics about these columns, such as the min and max values, and we put these statistics into the footer, along with byte ranges that allow us to specifically only load this very part of the data instead of loading the entire file. Then we do the same with the second row group. And once this is done, we have yet another footer for the entire Parquet file. And this footer contains information about the row groups. And now let's put this to a test. Now we are not the Parquet writer application anymore, but rather we are the Parquet reader application. So we have an on-disk format, on-disk storage, and now we want to read data from this. So what do we do first? We want to get column A, where B greater equals 3 in this case. So first what we do, we only read the footer, nothing else, just the footer. Given the footer, we know that row group 1's largest value for B is 2. So we can completely ignore row group 1. We never have to touch it. We can completely skip it. And this is called predicate pushdown. There's a filter condition, and giving this meta information that we have by the footer, we can completely skip scanning row group 1. And then in the second case, well, we need A and we need B for filtering. Then we have the projection pushdown, and both works with Parquet. This is not possible with CSV. There is no concept of metadata in CSVs. And that's a striking feature. And this is also a feature or an idea that is applied once again by the open table formats when dealing with lots of Parquet files. Okay, so I hope I have you convinced that Parquet is good. But there are some downsides of Parquet. For example, the Parquet specification does not contain anything about asset compliance. So if you have multiple write applications, transactions won't work. Performance and scalability. Once you have a lot of data, Parquet files themselves alone tend to be slow because of all this footer information. You have to query so much footer files in order to know where to look for your data. And also when it comes to schema and partitioning evolution, Parquet is not very flexible. And this brings us to open table formats. So on the left side, we have Iceberg as this Iceberg. On the right side, we have Delta Lake being this other animal. And in the middle, they are hugging Parquet because they're still using Parquet underneath. But now they're adding yet another meta layer on top, yet another footer on top to make it more efficient to work with Parquet. And the yellow box is all of the things that Parquet brought us. And the blue box are all the additions made by open table formats, such as schema and partitioning evolution, asset compliance, stream and batch processing. This is a huge thing. Incrementally process your data. And there's no need to have some external application to track what data has been processed or not in the future if you just rely on those open table formats because they have an internal versioning. Native maintenance possibilities, as we will see later, time travel, mutability, you name it. And how is that the case that now Iceberg and Delta Lake can manage all of these Parquet files, all of these little Parquet beavers in this case? And as I said before, they just add yet another layer of abstraction of metadata. And let's have a look for Delta Lake specifically in this case. What does the metadata of Delta Lake contain? It's like a transaction log, because you can see here on the left side a different path. Each path corresponds to a single Parquet file, and then the transaction log is like a binary log of a typical transactional database. Tells you, well, Parquet file 0 was added, and then we have some min-max values. We also have some partitioning information. But you can also delete files, and you can also change the schema with this DDL, data definition language. And then you can version it. And having different versions means, well, if I have a reader application, it remembers, well, last time I came here, I only saw the data of version 1. Now I have to read everything that has been added afterwards. So you have this incremental processing allowed. Time travel is now possible. And you keep all of this meta information in this single place. With Iceberg, it's a bit different. The idea is the same, but the structure is somewhat different. I won't focus here because I don't have that much time on it. So we skip this for now, and let's just see examples of transactions and time travel. One important note here, if you want to support transactions, you need to have some sort of external locking mechanism. For example, with Delta Lake, typically nowadays you would use a catalog that does it for you, but you can also rely on a DynamoDB table to do the locking for you. It requires some sort of atomic swap in order to make this new version be the newest one. Let's see a typical scan without metadata. So we have those 12 Parquet files, and we are only interested in reading the blue one. Without metadata, what our engines do, well, yes, I scan all of these Parquet files and their footer information, because I just don't know where the data is that I'm looking for. Well, however, if I have metadata available, such as for Iceberg and Delta Lake, what I do, well, first I read the metadata, and then I know where to go. Then I know, oh, it's there, and I only have to look there. 2 API calls. Even if you scale up, then it becomes very, very obvious that you have a huge benefit if you have metadata available. And the next one is not clearly related to Parquet, but more with Hive partitioning. Let's assume we have one partition and there's lots and lots and lots of small Parquet files there. First of all, you get a lot of metadata overhead of the Parquet files themselves. But also, think about the HDFS name node, for example. The HDFS name node is responsible for keeping a reference of each Parquet or of each file name to their corresponding storage location on the data nodes. And this HDFS name node has an in-memory presentation of this reference. And it's not unlikely that you run into an out-of-memory error because you just have too many small files. The same applies to our Delta Lake and Iceberg index, because they also have to keep track of all of these files. So this is not very efficient. And also when we think about cloud storage for analytical workloads is very efficient if you have large sequential reads. But in this case, you have many small reads. This is not very efficient. There's lots of overhead involved. So what you can do compaction. We just move all of these tiny Parquet files into one large Parquet file. That's the way it has been done in the past. But now let's assume there's a second partition, but this one only has less data. And then we also compact it, but then we have a different size of Parquet files here. It's not really our target size we're interested in. And this is a diagram taken from Databricks, and which showcases the difference between the fixed partitioning scheme used by Hive, which results in skewed file sizes, and the difference on how liquid clustering, as we will soon see, improves on that. In this case, yes, we hit the target size for some partitions, but some partitions are completely empty. And other ones, the newest ones, there are plenty of those small files that have not been yet compacted. And if you scale out, you still may run into a problem. There are lots of small files, and partitions are not evenly balanced. In this case, you can apply liquid clustering. It allows you to have flexible partitions and equal file sizes. And as we see, for example, in this case, in the US in February 2023, we now just create more partitions instead of having one partition with lots of data. And this is what I meant earlier with maintenance improvements. Liquid clustering has a specification, is not implemented in every writer application, but when you use it, it can improve your quality of life as a developer. So, promises made. Reduced maintenance, improved performance, more flexibility. Let's go for it. And for us, we wanted to substitute our Parquet-based read-only Bronx layer with Delta Lake. So, put it to a test. Under investigation, liquid clustering. Because it seemed so attractive to us to use liquid clustering, since our Parquet files, we also suffer from a small file problem. Our Parquet files typically have a size of 4 to 5 megabytes. That's not enough. So what we did, we had a setup in which we used 1.3 terabyte of session files. You can imagine a session file containing a machine number, a timestamp, and then some arbitrary information. That's the most important part for you to know. And then we have, on the left side, classical Hive partitioning, so fixed partitions, and on the right side, we have liquid clustering. And then there are also two important distinctions here. We did this benchmark while processing the entire 1.3 terabyte at once to create the data lake table with liquid clustering, which does not really apply in our day-to-day work, because typically we process roughly 50 gigabytes per day, and then we add it incrementally to a data lake table, and then it has to be clustered. You will see why this is important. So let's take a look at the very first example. So we read 1.3 terabyte of data and write it to data lake with liquid clustering, or we have it with Hive partitioning. Let's look at the chart. On the y-axis, you see the total number of API calls required to fulfill a query by machine and timestamp. So we query just a random machine, and then also provide an additional filter on the time span. And then you see is it orange for you? Yeah, it's orange. The orange bars, they correspond to Hive partitioning, and the blue bars, they correspond to liquid clustering. The lower, the better. And we can see, as expected, given that we have metadata information available, flexible partitioning, liquid clustering is clearly the winner. Another KPI, the total duration taken by those API calls. And yet again, we see liquid clustering is clearly better. So is this really the better life? Well, we thought initially, it was like, yeah, hooray, talking to my manager, we can improve here, we can save a lot of money. And then I did another test using the incremental ingestion. So in this case, not reading 1.3 terabyte at once, but only 50 gigabytes, and then adding it to a data lake table and clustering incrementally. And all of a sudden, the effect almost turned around. So liquid clustering got worse, even worse than Hive partitioning. And in this case, with the total duration, it's actually worse than Hive partitioning. And that was a huge surprise for us, because the promise of liquid clustering is, well, use liquid clustering. You don't have to care about clustering anymore. We do it for you in the background. So obviously, it fails to properly rebalance the partitions with default parameters. So we reached out to the Databricks support, running this on a Databricks runtime. And they told us, well, there is a configuration property that it's not publicly documented, but you can use to tweak how liquid clustering behaves. All right, so we did this, and yes, it worked then. But it doesn't hold up to the promise that you just relieve the developer or the data engineer from manually clustering and manually observing performance of your table. And what's even worse, in my opinion, is currently there is no way to access the clustering health of the table. And when should I use this skewness threshold? When should I apply it? And they're saying themselves, well, without a method to monitor it, it's difficult to determine when to exactly use this. So this kind of left me unsatisfied. And just to make a comparison here, Snowflake proprietary format, I'm not a big fan of proprietary formats, that's why the talk is about open table formats. For their internal proprietary format, if you use clustering, it's kind of a similar thing that liquid clustering does. At least they have a method that you can use to see whether the table is clustered well or not, given certain columns. Okay, the second thing under investigation, the idea of interoperability. How well is Delta Lake supported out there in the Python and cloud ecosystem? The idea is write once, read everywhere, naive defaults. What we did, we used Databricks runtime 15.4, LTS, and stored it on S3, and then we provided access to the S3 bucket to all of these different engines and wanted to see if they can just read and operate with the data lake table. So we use DuckDB, and you can see, well, DuckDB, at least it knows the schema, but empty data. This was not successful. We used polars, and oh, there's an error, an exception, Delta protocol error. Certain features are not supported. Okay, column mapping, V2, checkpoint, deletion vectors. I didn't know about them before. Then using pandas, the same error message. That's because they're using the same Rust kernel underneath. With Amazon Athena, the clue error just spit out an internal error. I don't know. With Snowflake, empty table. So this was not really satisfying. So could you say write once, read nowhere, and say in defaults? Turns out, Delta Lake has table features. I'm not here to bash Delta Lake or Databricks. Don't get me wrong. I'm just saying you have to get your head around and understand what's going on. On Databricks, you get the newest table features available, and they're activated by default. But if you want to use open source engines to read the data, most of them do not support them yet. And sometimes, at least for me as a user, it was confusing to see which one is supported, which one isn't. And also, you find this kind of strange that on this slide, this parameter here, it says spark.databricks. And even the open source Delta Spark implementation has spark.databricks. Why is Databricks there? I thought it's Delta Lake open source. So this is kind of confusing. Anyway, so tweaking this Delta Lake table, removing certain features, finally brought us where we wanted to be. Now we have a DuckDB reading the data successfully. With polars, somehow there is still this timestamp with native time zone, so not a time zone aware timestamp. This is not supported yet with polars and pandas, but Amazon Athena finally worked, and also Snowflake worked. So as a result, mind the difference. You have to know which features you use. And the last one, this is rather special in our case. We wanted to do incremental processing. We had like a manual framework for this in the past, and we wanted to ditch it because development work, maintenance work, and so on. And there's one important thing to understand in our case is that when a printing machine boots up, and until it runs, until it shuts down, a single session file is created, a single Parquet file is created. And to make developer life more easy, we wanted to just reason about entire sessions instead of reasoning about partly available sessions. So instead of having a streaming framework, we wanted to have batch processing because batch processing is both more efficient and easier to write and easier to test than streaming. So we wanted to preserve these session boundaries. And what you can do on Databricks, you can use autoloader. And autoloader works perfectly with file semantics, incrementally loading entire files. This is very similar to what Snowpipe does on Snowflake. And if you use autoloader, it's just fine. You can stream entire files, entire sessions into your Spark streaming context and then apply a batch processing procedure on top of it. Perfect. But we thought, well, maybe we can just go without autoloader at all, just rely on pure Delta Lake open table specification because there is incremental support available. But it turns out Delta Lake has table semantics. These session boundaries that we had via entire Parquet files, they're not preserved. And this is by design. There is no way around. We also reached out to Databricks support, and they said, well, your use case is nowhere near the design of Delta Lake or open table formats in general. So this was also kind of not really satisfying, but it's like a homemade issue that we have. So summing up, we wanted to go with Delta Lake because of all of these promises, but then realized, well, liquid clustering didn't hold up the promise. Interoperability was still challenging. And also our specification to preserve session boundaries is very specific that can't be really forced into the design of open table formats. Iceberg and Hudi also won't solve this for us. Okay, so that's so far for Delta Lake and Parquet. Now a few words about Iceberg here on the left, our left contender, and Delta Lake on the right. I left out Hudi because Hudi is more focused on streaming workloads, even though we can do batch processing, and also left out Apache Payment because this is rather new, coming from the Flink community, and which is also more focused on streaming workloads. Let's have an example of the main contributors to Delta Lake and Iceberg. I did this roughly 2 weeks ago, so it's representative. And on the left side, we see all of the contributors to Delta Lake. And even the first one is someone from Databricks. And it's almost exclusive people from Databricks. Whereas if you look at Iceberg on the right side, you can see many different names. And a lot of these Gmail addresses or names, they are from Dreamio, they are from Starburst, they're from various companies. And you can see that the community engaged with Apache Iceberg is more diverse, being supported from many different companies, whereas with Databricks, it's almost only Databricks at the moment. Secondly, if you think about the overall community engagement with these two table formats, just 2 weeks ago there was the Iceberg Summit for the second time. 1 day in person and 1 day remote. It's being supported by many different companies, from Dreamio, Snowflake, AWS, Microsoft, also Databricks. And there's like a whole own summit dedicated to Iceberg. And if you look something for Data Lake, well, the only thing you will find is the Databricks AI Summit in June this year. And those are the 5 talks that popped out after a search for Delta Lake. That's not a whole lot. So it seems from the community perspective that Iceberg has an edge. And there are also other cloud developments such as S3 tables being announced by AWS natively supporting Iceberg. And yet another note, Databricks bought Tabular last year. And Tabular was one of the main pushing forces behind Iceberg. And we wanted to enable true interoperability with our Databricks runtime and Iceberg. So one thing you want to do is having an external data catalog, connect to it, and write Iceberg format natively with the Databricks Spark runtime. But it turns out that even though vanilla open source Spark is able to do this, the Spark runtime on Databricks isn't. And at least for me, this was disappointing. Yeah, to be honest, it was just disappointing. You can use vanilla open source Spark. It can do so. But the Databricks runtime, a managed enterprise Databricks Spark runtime can't. It's on the roadmap. You can read Iceberg data from external catalogs if you integrate them, but you can't write data. And that's disappointing. Yeah. So in the end, I think it doesn't matter if it's Iceberg, Delta Lake, Hudi, or whatever. In the end, open table formats, they make our data engineering life better. Just remember a few years ago, if you use Snowflake, Redshift, Google BigQuery, whatever, your data, our data, is locked behind proprietary data formats, and it's only accessible via proprietary cloud engines owned by vendors. So the entire ecosystem is changing. Now we're using open table formats such as Iceberg or Delta Lake, and we're not relying on any proprietary formats anymore. And it's our data, and we can access it with any engine we want. We are not forced to use the Snowflake compute engine or Databricks Spark runtime. We can use DuckDB, we can use Polars, Pandas, whatever, Data Fusion, also to name it. And I think that's a great thing. That's a great future ahead. That's also the reason why this Iceberg animal and the Delta Lake animal, they have the same logo right here. Doesn't matter if it's Iceberg or Delta, who cares? Just have open table formats, making our data available, removing or reducing the lock-in that formerly cloud proprietary data warehouses such as Snowflake and Redshift had. And this is my closing statement for today, and thank you for attending. I'm curious for your questions.
So thank you for the talk, Franz. The first question is not actually a question. It's just the audience that wanted to say that they loved your visuals that you introduced into the presentation. So the first real question is if you could elaborate on DynamoDB for locking files as opposed to using Polars, Unity, or any other catalogs. Is there any conscious trade-off?
Well, if you want to use DynamoDB just for locking, you just use it for locking. I think don't use it. It's just there that you can use it to enable transactions, to enable multiple processes to write to a single Delta Lake file. It's very similar. If you, for example, have used Terraform, you also need some sort of locking mechanism that you don't overwrite or corrupt this Terraform state. It's the same idea. You just need some external criteria to tell you whether you can write to this metadata or not. It's just a lock that you use. And in this case, it's DynamoDB. But I would always rely on a true data catalog, such as Polaris, for example. Yeah.
Would you say there's something like liquid clustering with Iceberg tables?
It's an interesting question. I also thought about it, and I think currently there is no implementation for this, but there could be an implementation. Given that Iceberg also allows partitioning evolution, and since partitions are just metadata in the hierarchical metadata file of Iceberg, there is no reason why not to have liquid clustering for Iceberg. Yeah.
And if you had the chance today to magically migrate your data stack to Snowflake or Databricks, which one would you pick, or both?
Ask me afterwards, not on stage.
Okay. So is there any reason why you chose specifically DynamoDB for cataloging?
We didn't choose it. I just mentioned it that you can use it. We're not using DynamoDB for cataloging. It's just for if you require a locking mechanism, then you can use it. But we don't use DynamoDB for locking or as a catalog.
And yeah, so I think another question goes in a similar direction. If you have different data in Delta and in Iceberg, and if yes, how do you tackle data governance? And if no, how do you keep indices in sync?
So if you have both Delta Lake and Iceberg, and how to keep them in sync, or didn't quite get the question?
Yeah, how to keep them in sync, and how do you have data governance, because you need to account for both platforms.
So ideally, you have a single data catalog. And this data catalog is independent of a cloud vendor or like, let's say, Databricks or Snowflake. Think about Polaris, even though it has a strong affiliation with Snowflake. Lakekeeper is a great example, a data catalog written in Rust. And then with Lakekeeper as a data catalog, you can manage both your Iceberg and your Delta Lake tables. There is no contradiction in doing so with both. Yeah.
Why didn't you add the session boundaries into the data? Instead of having the boundaries as a file, it could be identified by an extra column.
Yeah, good question. We do have the session boundaries within the file itself too, which is just the name of the log file. However, if you have it within the session file, then you have to take care yourself within the streaming context to remain history and to track history and to decide at which point is this session complete. So this is, once again, you start your manual custom framework in order to preserve these session boundaries. And that's something we didn't want to do. We just wanted an out-of-the-box solution, but this failed. And if you do this with Spark streaming, maintaining your own Spark context, your own history, then you get very close to what we had before. And we wanted to ditch this.
And we still have time for last two questions. So why do you create the session data on customer appliances instead of streaming the data directly via AWS, Firehose, Azure Event Hubs, or other?
Yet another great question. Actually, we do both. We already stream the data, but we only stream high-level KPI data, telemetry data. But with those log sessions, they contain very row-level information. You can like pin a certain module in a given printing unit, very down to like on some board where this message originated from. And if we would stream all the data that we have in our log sessions, this would be just too expensive. And there's also a technological point that this may not even be possible with our architecture to stream everything. Yeah. So it's a trade-off. Batch data for things that are not time critical, but we stream data for time critical applications.
And then as a last question, what are your thoughts on S3 tables?
Well, I think it's a good decision. They went for 3 tables by AWS. In the beginning, I was a bit disappointed because at 3 tables, they promised interoperability. But in the beginning, you could only use it with a custom Spark wrapper given by AWS or created by AWS, or you had to use the AWS Clue catalog. So you're forced to use the Clue catalog. You can't use Polaris or Lakekeeper to connect to the data, but they've changed this just recently, I think 1 or 2 weeks ago, that now the S3 tables also support natively the Iceberg REST API for data exchange. This is really great. Yeah, I think this will be a game changer, even though also to add the functionality of the S3 tables in maintenance, like compaction, is still very limited. It only supports bit packing, it does not support sorting or Z order, and it also does not support incremental compaction. So typically what you want to do, I just compact the data I got from yesterday, but not the entire table. What happens if you change the size, the target size? Does it compact the entire table again? This would be hilarious. But you only want to compact the data that arrived like yesterday and not more. And this is also not possible at the moment. So it's still limited, but I think the direction is good. I think cost-wise, I can't really judge, but from what I've read, it's fairly expensive in comparison if you do it on yourself or by yourself. Yeah.
So thank you for the talk and for the answers, Franz. There's still a few questions asked. Maybe you can come to the front later, or you can answer them on Discord if you want.
Or join our booth, yeah.
Yeah, or join him at his booth. So thank you for the presentation, and yeah, thank you.
Thank you.